Give me options. That would be cool. All right.
Are you okay?
Okay. I'm trying to hug random people.
Mom is it?
All right. Probably not the best thing, but we'll worry about that later. All right, let's talk about number 6 because Kara said number 6 was a problem, and we're getting ready for a quiz today, so that would be cool. Number 6. Number 6 says, I'm starting at some place where the electric potential relative to infinity, which is how we know these things, is 6 volts. I'm going to move it to the place called land of negative 10 volts. Okay, and I'm grabbing a whole bunch of electrons. I'm taking a package of electrons in a little pocket, and I'm going to take them from here to that spot there, from this spot all the way to that spot there. Agreed? How much work is done doing that? Is that the question asked? So what? How much work is done? How much work is done? So work is equal to energy. But just in this case, it'd be for voltage and charge, energy is VQ, right? So the work is going to be equal to the voltage change. What's the voltage change? 16. Specifically negative 16, though, because I went downhill. And then what's the charge I'm dragging that distance? Well, Avogadro's number is 6.02 times 10 to the 23rd. Times the number charge of a singleton electron. What's the charge of a singleton electron? It's on the formula sheet. Oh, gosh, I didn't write formula sheets for you guys. That's a problem. What was I doing? No, you have to get out their own formula sheets. Hope you got them all. Charge an electron?
1.6 times 10 to
Negative 19? Okay. Throw that in all my calculated equals, and I should have an answer. How much work it takes to drag from one place to the other place. All right, this is work equals VQ. All right, and then what was the other one you asked for? 13 you said you had?
Yeah.
20, so it's back? Just do the back?
Yeah, we do the back.
Is there anything in the front still? Anybody got a problem with the front problems at all? Peter, front problems, any problems? No. Yeah, you wouldn't know.
I actually did the front though, so.
Okay, that was the hard part. Although the back part is better review. All right, so number 1 metal sphere, and it's got a metal sphere of radius R, capital R1, and then I've got a hydrogen Q charge. It's a metal sphere, so it's all going to range on the outside. Agreed? It's metal. Metal means conductive in this class, regardless of whether or not that's true. What is the potential difference between R2 and infinity? So I want to find my potential between R2 and infinity. R2 is at that point there. So Peter, what's my approach? Not how to do the problem. What's my approach? How do I find voltage?
I feel like we're going to use KQ or D squared.
Not in this case, no. Well, although you could, let's not do that.
Oh, it does work.
Yes, it does. But if I gave you a different shape, it wouldn't work. So let's just pretend for the moment. Let's do one that works for you. My general approach is what?
Something that involves distance.
I need the electric field, don't I? Because I'm going to take, to find voltage, I'm going to do negative the integral of electric field. Back to distance. Now, let me pause there. I want to make sure Peter's got this. Does that make sense? Our approach for voltage is going to be what's the electric field? Integrating to get voltage. Okay? So to find the electric field at this point around a sphere, what am I going to do, Peter?
This is the charging closed one.
Yeah. Gauss's law, most important thing to check.
Oh, that.
Oh, that. So what you do is charge enclosed over E naught is equal to the integral closed integral of E dot dA. You're going to do that for sure because you know that's worth a point probably. 9 times out of 10 worth 1 point. Good news, you have to write it down one time. There's like 4 questions that you have to do. Is it on? You have to write down the first time you get the point.
And you don't have to do it like the next.
No, you have to write it down the next 3 times. Yeah, I assume it's okay. Just have to get it down there. And by the way, if you do it on the 3rd one, and you need it for the 1st one, they still get that point. They look down the list, you go, they wrote it there, give them the point. Okay, so we ready to do this? I note that the shape Peter picked, I don't know if I asked Peter, what shape would I pick, Peter?
It's just a larger circle.
Larger sphere, 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 sphere.
Okay, it's a larger sphere, and then it's purple and equidistant and all that nonsense of sphere.
I know it's completely surrounding it. I know that the flux lines will be heading straight out from it. So they're perpendicular. And I know that, it's the third thing I know. There's one other thing I know. It's completely enclosed. And symmetric. The electric field is the same everywhere on the shape I drew. Right? Knowing all that, I can say EA is equal to Q enclosed over E naught. Q enclosed is going to be Q. Q over E naught equals, what's the electric field? I don't know. What's the area of the shape you drew? 4 pi r squared. Now again, we're going to leave it generalized. Why? Because we're going to integrate it in a moment, right? We need to write it as the electric field before I do that, so I move everything over. I got Q over E naught over 4 pi, and I'm going to write an r to the negative 2. Why am I doing that, Peter?
It'll make it easier to
Yeah, because I'm about to integrate it, right? Why not leave it where it's on top? Make my life just a smidge better. So now I'm going to do the voltage is equal to negative. I've got Q over E naught 4 pi r to the negative 2 dr. Yes, sir.
Is that R a random R or is that R2?
That is R from wherever to wherever. This is my electric field here, 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 anywhere. Now, I initially drew it to R2, and that was a mistake. I shouldn't have drawn it. Because we're going to try to integrate from infinity, we need all the R's. We need an equation that works from infinity all the way to R2. We actually don't need it anyplace else, but right now that's what we're going to do. Agreed? How do I integrate this, Peter?
you can pull everything out, right?
Pull all the garbage out because I don't want it. What's the integral of r to the negative 2?
Negative R to the negative first.
So negative r to the negative first. And we're going to integrate from where to where? Because I want the voltage between infinity and R2.
Is it not those points?
It's those points.
Okay. It made it sound like it was something weird.
So infinity, R2. So I'm going to plug these things in. Now to plug these things in, I'm going to have to clean this up a little bit. I get V equals Q over E naught 4 pi. 1 over R2 minus, well, that whole thing becomes 0, right? Because infinity is on the bottom. So you guys are jumping ahead, so I'll take it. And so this is going to be my answer for the voltage at that point. I check signs. Would it require energy to move from infinity towards a positive charge with a positive test charge? Did I get a positive answer? Good.
Wait, change energy?
It would take, I'd have to work to do it, right?
Oh,
So it would have energy stored when it got there, right? So the voltage is uphill. So I'm climbing uphill. I need a positive answer when I get done. Check that, because sometimes you'll do everything beautifully mathematically, but you'll have the wrong answer because you have the wrong sign. Check it. Okay? There's nothing, if you did R2 to infinity, you'd get a negative. But you know that's not right, and you did everything. The math is there. And again, on calculus, you have to go back and fix it where you made the mistake. In physics, no, that's got to be positive. I'm done. Eraser.
Okay.
Get rid of that minus. Just, that's enough. Circle the right answer. They'll go, this kid got to here, realizes the problem, change the sign, beautiful, all the points.
Okay.
Kid knows it's, and the physics people at the table actually argue, hey, they just chose to do it backwards. and then change the sign. That's totally fine. That's not what you did, but that's okay. That's what they do, and help you out. Good? All right, we got the next one?
Yeah.
I want to know between R2 and R3. So I'm going to take this same idea. I've already got the electric field, don't I? Between R2 and R3?
Yeah.
So I'm going to go ahead and do that, right? So I'm going to do the exact, yes, ma'am.
If you recognize that 1 over E naught 4 pi is J, would they accept KQ over?
Oh, absolutely. Totally accept that. Yeah. In fact, if you want to do all your Gauss with Ks, you're allowed to do that. I'm not gonna because they don't. But I totally allowed.
Okay.
100% allowed. In fact, I've seen keys where they do that, where like they're using E naught and suddenly they switch back to K. And I'm like, what are you doing? All right, whatever. Makes you happy. And then again, the other thing that could happen is this: is again, if you recognize this as a sphere, it's the same as a point charge concentrated at a point. This is dangerous. Don't generally assume this. But you could have used KQ over D squared for that one, and you get the right answer. You get the exact same answer. And they would totally accept that as another approach because you're recognizing from a physics point of view that that's equivalent. Having a sphere is the same as having a point charge, as long as you're outside the sphere.
Okay.
So that's allowed. Again, don't recommend that because if they're gonna throw a trick at you, you're not gonna pick that up by using that approach. Okay. All right. So I'm good there. And then the next thing so now I'm just the electric field isn't gonna change, right? The electric field doesn't change. Then all I have to do is integrate my new choices. So I'm gonna do from where to where. It says from R2 to R3. So I'm gonna R2 to R3. And then I go Q over E naught 4 pi R to the negative 2 dr. I would bother to write this down. You don't have to for the physics test. But I would write it down just in case you did something silly.
Okay.
Okay. But the rest of it's pretty straightforward. You can go ahead and because you already did this once, you just go Q over E naught 4 pi R3 minus, minus Q over E naught 4 pi R2. Right? Just plug them in. You already did the work. You already know how to do it.
And then that's where you would
That's your answer. And then I would check one more thing. I'd check signs, right? So I'm going from R2 to R3. Is that downhill or uphill?
uphill.
I'm at a positive charge. I got a positive charge at starting at R2 and going to R3.
Starting at R2.
And going to R3, right? So starting at R2
Yeah.
and going to R3. I'm going to take a positive charge from the positive thing. I'm going to move from here to here. Is that downhill or uphill? Would it want to go that way or not?
You don't want to go home.
We,
It would take work.
you'd have to push a positive charge to get to here?
No. It would, yeah.
It would naturally go that way, wouldn't it? So I should have a negative answer. So now I look at this and go, oh, do I have a negative answer? Well, this is smaller than this, right? So this is going to be a larger number when I divide by a smaller number, right?
Uh-huh.
So this is going to give me, I was thinking, hold on. Well, this is larger. So this is a larger number, right? So it's a larger number. It's going to give me a smaller number. This is going to be a larger number. So therefore, it's going to be negative, which is what I expect. Okay. But I would check. I would check that every single time. I would. Just as such.